Our first talk will be Enabling Immersive Experiences in Challenging Network Conditions by Mike Luby.
Good morning. Yes, I'm CEO of BitRipple, and I'm going to be speaking about enabling immersive experiences in challenging network conditions. So the problem that we are focusing on are things like remote collaboration and defense communications. And the thing that we're focusing on is providing these immersive experiences where you have to deliver lots of content with tight latencies. So that's the kind of problem that we're focused on. So for example, remote collaboration, you can think of you're kind of surveilling an autonomous drone and you kind of want to see where it's going and so on. Or you've got an autonomous vehicle out there and it's, it's like a tractor. And you want to make sure when it's plowing the field it doesn't run into a rock or whatever. So you really need to get the feedback really quick. And a bunch of defense applications as well. So in remote collaboration solutions, you have these distantly wirelessly connected devices, and as everybody knows, wireless networks can be sometimes an issue. So the problem is to really deliver large amounts of data in a short period of time. And for streaming is to provide, the problem is that sometimes with existing solutions, the streaming can be pretty low quality and sluggish responsiveness. So a better way to move data, and I think I talked about this last time, but there is new material this year, so just hold with me if you were here last year, is to use forward error correction, in particular the RaptorQ forward error correction code standardized in the IETF in RFC 6330. And the basic idea is for every data object that you want to get from the sender to the receiver, so we take all the data and package it up into objects. So you can think of an object, for example, as a frame of video or a small set of data that you want to get from the sender to the receiver. By the way, the clock didn't start, so I have no idea. I have unlimited time. That's good to know. So the basic idea is you want to get this data from the sender to the receiver, and of course you can experience packet loss. So what we do is we use the RaptorQ to generate encoded data that is sent across the network that is an encoding of each of the objects. And the key property is that this encoded data is both expandable and interchangeable. Expandable simply means that you can generate as much of this encoded data as you want from the data object. So you can kind of dynamically adjust how much you're going to send across the network. And that it's interchangeable means that at the receiver, it doesn't matter which portion is received, as long as enough is received, which is the size of the original object, you can recover. So it gives you a lot of flexibility as well. By the way, I realize this is probably an old version of the talk. I think I had a newer one, but this one, oh well. So the high-level protocol idea is to send an amount of encoded data for an object so that the amount received is slightly more than the object size. And this is adjusted based on feedback from the receiver to the sender, based on, which I'll talk a little bit about in another slide in a couple of minutes. So the feedback gives you ability to measure the current packet loss, and so you adjust the amount of, dynamically adjust the amount of encoded data you're sending across the network for the objects. With this kind of solution, you never retransmit. If you need to send additional encoded data, you just generate it. It is, after all, a fountain code. So if feedback warrants this, you just send more encoded data. And the objective, of course, is to obviously minimize the delivery latency of the objects, but also to minimize the bandwidth used to deliver the objects. You want to kind of minimize that bandwidth. Subject to the constraint, you're also minimizing the delivery latency. Some more details in terms of how our protocols work. The data packets headers contain global sequence numbers, very similar to what QUIC does. There's other data in the packet headers that contain information about the object, its ID, its size, which encoding symbol is carried in that particular packet, and so on. The feedback packets from the receiver include things such as the highest global sequence number received, the number of packets containing encoded data received so far, and for each object that's active, how much encoded data has been received. And based on all this, you can calculate the packet loss and how many more packets to send for each object, and so on. So the sender uses all this feedback. All the logic is really on the sender side to estimate the packet loss rates and to adjust how much more encoded data to send for each object, and so on. So this simulation I actually showed last year in MHV. So this was just a simulation, a very simple kind of model. And what it essentially showed here is with this kind of protocol that we had, you're able to minimize the under varying packet loss conditions. You're able to minimize the amount of bandwidth you're using compared to a retransmission solution. That's what's shown in the upper right graph there. So the blue line there is our bandwidth versus the orange is the retransmission-based solution. And the bottom graph is the delivery latency. And here we're comparing our solution against an optimal retransmission solution that is optimal in the sense that it's sending packets as soon as they're noticed that they're missing, and so on. And so you can see that with our solution, we're able to minimize the delivery latency, whereas with retransmission, it varies depending on what packet loss conditions are. So now, this is going a little bit beyond what we did last year. We actually have the software at this point. So we have done some trials with it, obviously. So for this particular instance of the software, there's a memory-based interface, which essentially means that data objects are stored in memory and they're passed in through a pointer to our sender. And then it takes that object and does all the encoding and sends it across the network based on feedback and so on. And then once it's recovered at the receiver, it's passed back to the receiving application through memory as well. The reason it's through memory is obviously that reduces latencies and so on. So this graph needs a little bit of explanation. This is our software running in practice. We have both the sender and receiver running on the same machine. We're sending packets from the sender to the receiver via a local loopback, and we're actually inducing packet loss on that as we're sending them. And so what this is measuring is the time between when an object gets to the sender, passed through memory to the sender, till when it's finally been recovered and it's being passed out of memory at the receiver. And so in this example, we kind of did different object sizes ranging from, they're called frames here, from 20K up to around 100K. And those, if you're operating at 60 frames per second, those correspond to streams ranging from 10 megabits per second up to 50 megabits per second. And so what it shows is all the time we took for bringing the object in, doing the encoding, the packetization, sending the packets, inducing the packet loss, recovering the packets, recovering the objects, and so on, takes less than 2 milliseconds overall. So the point here is that the void error correction is not adding latency to the solution. It's kind of the message. So here's some actual results. Oh, now I have a timer. Is that accurate? Okay, good. Good, then I'm going to be fine. So these are some actual results of the software running. By the way, I should have said on the previous thing that was a Windows-based platform, just a standard kind of platform there, where there was just one thread being used for the sender and one thread being used for the receiver and so on. So these are some results where we're sending it across the network. We induced a 40 millisecond round trip time in this case. We have spiky losses, so that's shown in the bottom graph, that red line that goes straight across and up and down and up and down. So whenever it goes up, it's spiking up to 3% packet loss, and that's mapped against the right side of the graph there. This is about a 10 megabit per second stream at 30 frames per second, so each frame is about 40 kilobytes. And what is shown in the bottom graph in the green is how much of the encoded data we're sending over time, where 1 is normalized to the size of the original object. So you can see at the beginning it's pretty flat, and then when the packet loss goes up a little bit, it automatically adjusts and sends a little bit more, and then goes down and up and down and up and down, adjusting according to the current network conditions. The middle graph actually shows how much is received at the receiver of the encoded data. That's what that blue line going across is. And as you can see, it's a little bit flatter than the green on the bottom, and that's clear because you had some packet loss, so you lost some of the packets, so not everything got there, right? And then the key punchline is the top graph, which shows the end-to-end latency of the delivery of these objects. And you can see it's pretty closely pegged to the minimal possible of 20 milliseconds. Since the round trip time is 40, the one-way delay is about 20 milliseconds. So that's one set of results. This is another set at a higher bit rate. So again, these are immersive applications. There actually are gaming platforms out there right now where to mobile receivers, they actually send 100 megabits per second. So I think one of the comments I got when I got some comments back on this work was, these rates are way too high. No, they're not. These are actually out there at this point. So this is a 100 megabit per second stream, 30 frames per second. In this case, it was we did a mix of different size frames. So 1.25 megabyte frame followed by 5 250 kilobyte frames, and just keep repeating that pattern. Same RTD, and so on. The loss pattern is a little bit different here. It went, started nominally small, and then it kept spiking up to 11% here, and then back down. And as you can see, again, at the transmission of the encoded data on the green on the bottom automatically adjusts according to what's going on. And you can see the blue in the middle, that's flattened out version of that because of the packet loss. And then the top, again, is the delivery latency, which is a little bit higher here because there's more data you had to deliver over the network, so it actually takes a little more than 20 milliseconds to get that data across. But still, it's pretty close to the, it's pretty close to less than 30 milliseconds all the way across. Okay. So we actually demoed this at NAB recently, a slightly different interface, more of a tunnel interface where we just have packets coming in on one end of into the sender and coming out on the other end. And it was pretty successful. So future work. What am I going to talk about next year if I'm allowed to come back here again? One thing that seems to have some pretty interesting interest in is multiple interface delivery. And what that means, instead of sending the packets along one path from the sender to the receiver, in some of these applications, they want to be able to use multiple interfaces, right? And the reason for that is for robustness and to get a better quality of service, right? One of the paths might be weaker. You're out in the wild somewhere, and there, you might have 5 different carriers, and you're trying to send packets over all of them back to where you're trying to put everything together. And so that one seems to be driving some pretty, and this the encoded data solution is really good for that because, again, it doesn't matter which packets arrive on which path at the receiver, you just put it back together. So long as you get enough, you can recover. Obviously, we need to add rate control protocols into this, right? Right now, it's not integrated in there. We fix the transmission rate at the sender, and it kind of sticks to that, where the transmission rate is the overall rate of the original source plus the repair data. And then overall design. This is a bigger project, the last one. Overall design of transport and network policies focus on minimizing delivery latency, design of network buffering policies. So there's some interesting, one of the reasons that packets are slow to be delivered across the network is because of the buffer policies and the routers and the switches along the way and how that's all working. So it'd be interesting to kind of do a higher level design of how this whole thing should be designed together, so to speak. So the interactions between this type of delivery and network policies. And that's pretty much it. So I have exactly 1 minute left, as you said I should have. So thank you.
All right. Any questions from the audience? Okay. Can you use the mic over there?
So I think one of your stated objectives was efficient use of bandwidth.
Yes.
Isn't it true that with forward error correction, you're sending redundant data even when it's not needed? So sometimes retransmitting on demand is more efficient?
Yeah, no question about that. So it depends on whether your objective is, if you have an application like, let's take an example, cloud gaming, sorry. What's more important, using 3, 4, 5% more bandwidth, or giving that end user a better experience, right? And so there's a trade-off there. I agree. So the idea with our solution is to minimize that bandwidth overhead to the minimal possible with the forward error correction, with the focus on delivering that minimal delivery latency, which is key to an end user experience.